What you're looking at here is one of the most expensive and least understood machines in the hydrogen economy. This towering structure is called a cold box, and inside it, hydrogen is cooled to an astonishing minus 253 degrees Celsius. At first glance, it looks like another industrial building filled with pipes and steel, but this machine performs one of the most difficult tasks in modern engineering. It removes nearly all thermal energy from hydrogen until the gas becomes a liquid. Large export-scale cold boxes can cost well over $100 million and represent the heart of an entire liquefaction facility. Every kilogram of liquid hydrogen used for export, shipping, aviation, or large-scale storage depends on systems like this. Today, we're going inside the machine that makes liquid hydrogen possible and discovering why so much money, engineering, and infrastructure depends on reaching one of the coldest temperatures humans have ever engineered. What you're looking at here is the reason liquefaction exists. On the left side of the screen, 1 kilogram of hydrogen gas occupies an enormous volume. The visualization shows a giant cube representing hydrogen at atmospheric conditions. Hydrogen contains a lot of energy by weight, but very little energy by volume. On the right side, the same kilogram of hydrogen has been converted into liquid hydrogen at minus 253 degrees Celsius. Notice how dramatically smaller the storage volume becomes. The image highlights roughly an 800 times reduction in volume. That transformation changes everything. Suddenly, hydrogen can be transported economically across oceans, stored in large quantities, and delivered to industrial users. Without liquefaction, many future hydrogen supply chains would require impractically large storage systems. The journey from that massive gas cloud to the compact liquid tank is what the cold box is designed to achieve. What you're looking at here is the temperature journey hydrogen must take before it becomes a liquid. On the left side of the screen, hydrogen exists as a gas at around 15 degrees Celsius. The molecules are moving rapidly and remain relatively far apart. As the temperature drops through 0, minus 50, minus 100, minus 150, and minus 200 degrees Celsius, the molecules gradually lose energy. Yet hydrogen still refuses to become a liquid. Only when engineers reach approximately minus 253 degrees Celsius does hydrogen finally condense into liquid form. The visualization on the right shows the molecules packed much closer together. This is the critical temperature that makes liquefaction possible. Achieving it requires extraordinary engineering, because minus 253 degrees Celsius is only about 20 degrees above absolute zero, one of the coldest temperatures encountered in industrial operations anywhere on Earth. What you're looking at here is the actual machine responsible for creating those extreme temperatures. Notice the enormous size of the structure. The graphic highlights a height exceeding 30 meters and a cost that can exceed $100 million for large export-scale facilities. Inside this cold box are heat exchangers, refrigeration circuits, expansion systems, cryogenic controls, and liquefaction equipment, all working together. Hydrogen enters the system as a gas and gradually moves through multiple cooling stages until it emerges as liquid hydrogen. The blue flow paths shown throughout the structure represent the energy journey taking place inside. This isn't simply refrigeration. It is one of the most sophisticated thermal management systems ever developed for industrial gases. Every pipe, valve, sensor, and exchanger inside this machine is designed around one goal: removing enough heat to reach minus 253 degrees Celsius. Now we're looking directly inside the cold box. Notice the 4 major stages highlighted in the center of the image. First comes pre-cooling, where the hydrogen temperature begins to drop from ambient conditions. Next comes deep cooling, where larger quantities of heat are removed through advanced heat exchange systems. The third stage is cryogenic cooling, where temperatures approach the extremely low values needed for liquefaction. Finally, the process reaches minus 253 degrees Celsius and hydrogen transitions into a liquid. The reason the cold box is so large becomes obvious here. Thousands of square meters of heat transfer surfaces are required to continuously remove heat from the process stream. The plate fin heat exchangers, refrigeration circuits, expansion systems, instrumentation, and temperature control systems shown throughout the image must all operate with extraordinary precision. Even small inefficiencies become significant when operating this close to absolute zero. What you're looking at here is one of the most important pieces of equipment inside the liquefaction process, the cryogenic turboexpander. Hydrogen enters the machine at high pressure and extremely low temperatures, around minus 150 degrees Celsius. As the gas expands through the turbine, it performs work on the spinning blades. That expansion removes energy from the hydrogen and causes the temperature to fall even further. The image shows the transition toward temperatures between minus 200 and minus 253 degrees Celsius. This effect is one of the key sources of refrigeration inside a hydrogen liquefaction plant. Notice the incredible precision engineering involved. These turboexpanders can rotate at speeds between 30,000 and 100,000 revolutions per minute. At those speeds, even tiny mechanical imperfections become unacceptable. Yet these machines must operate continuously while helping drive hydrogen toward liquefaction conditions. This image shows exactly where the money goes. Starting at the top, hydrogen enters the process as a gas. It then moves through compression, pre-cooling, cryogenic refrigeration, turboexpanders, and finally liquefaction. Each stage adds complexity, equipment, energy consumption, and cost. Compression requires powerful machinery. Pre-cooling requires heat exchange systems. Cryogenic refrigeration demands specialized refrigeration cycles. Turboexpanders require precision manufacturing. Finally, the liquefaction stage itself pushes engineering close to the limits of thermodynamics. The graphic also highlights a critical number. Producing liquid hydrogen typically requires around 10 to 13 kilowatt-hours of electricity per kilogram of hydrogen. As engineers approach minus 253 degrees Celsius, every additional degree becomes increasingly expensive. This is why liquefaction plants represent some of the largest capital investments in the hydrogen economy. What you're looking at here is the hidden supply chain behind every cold box. Notice the different systems surrounding the central structure. Heat exchanger manufacturers provide the thermal heart of the system. Compressor suppliers develop hydrogen compression equipment. Valve and control manufacturers deliver process management systems. Refrigeration specialists create the cooling infrastructure. Turbo-expander manufacturers supply the machines that generate additional refrigeration. Instrumentation companies provide monitoring and automation equipment. On the left side of the image, you can see the broader industrial network, including equipment manufacturers, material suppliers, cryogenic specialists, EPC contractors, automation companies, and engineering firms. No single company builds an entire cold box. Instead, hundreds of suppliers contribute thousands of components that must work together perfectly. The final machine is the result of a global industrial ecosystem. This image illustrates one of the biggest risks facing hydrogen projects today. Notice how nearly every part of the facility is complete. Civil works, foundations, structural steel, piping, electrical systems, storage tanks, and even the cold box itself have been installed. Yet the project remains incomplete because one critical component has not been delivered. The highlighted example is a cryogenic turboexpander with a lead time of 52 weeks. On the right side of the image, you can see other critical items including cryogenic compressors, heat exchangers, control systems, and specialized valves. If any one of these components is delayed, the entire project can be delayed. This is why hydrogen developers increasingly focus on procurement strategy, supplier relationships, and manufacturing capacity. The challenge is no longer simply building the plant. It is ensuring every critical component arrives on time. What you're looking at here is the global race to build more cold boxes. The map highlights major hydrogen development regions including North America, Europe, the Middle East, Asia, and Australia. Across all these regions, governments and companies are investing in hydrogen exports, sustainable aviation fuel, industrial decarbonization, energy storage, heavy transport, and global energy trade. The challenge appears on the right side of the image. Manufacturing capacity remains limited, lead times remain long. Specialized suppliers remain relatively few. Skilled labor shortages continue to affect deployment schedules. The entire hydrogen economy depends on expanding the manufacturing base capable of producing cold boxes and other cryogenic equipment. The future panel shows what success looks like: more factories, more suppliers, faster deployment, and true global scale. Hydrogen growth ultimately depends on scaling the industrial supply chain behind these machines. What you're looking at here is the complete hydrogen value chain. Starting with water, hydrogen is produced, compressed, liquefied, stored, transported, and finally used across multiple industries. The cold box we explored throughout this video represents only one piece of a much larger engineering ecosystem. Understanding that ecosystem is becoming increasingly important as hydrogen projects move from demonstration scale to commercial deployment. H2 Hub by Renee Energy was created specifically to help engineers, students, developers, and energy professionals understand these real industrial systems. Inside H2 Hub, you'll find expert-led courses, practical engineering knowledge, hydrogen system deep dives, real industrial use cases, and industry insights focused on the technologies shaping the future hydrogen economy. If you want to go beyond headlines and understand how these systems actually work, visit H2 Hub, reneeenergy.com, and start learning today. The future of hydrogen belongs to those who understand the infrastructure behind it.